And okay, the recording, perfect, excellent, and hopefully people will start joining now. Excellent. Let's wait a minute or two, and people will come. Ah, sorry, I was wondering what is popping up. It's your iPad.
Yeah.
Okay, people are coming. Excellent. Let's wait a minute so that we are all ready. Okay, the first slide looks very interesting.
Yeah, we're gonna, I mean, today I decided to kind of go for bird's eye view on what I've done with it and kind of what people can do with it, what I think at least people can do with it, with this geometric approach.
Yeah, fantastic. Then I think we waited a minute or so. I think we can start. Yeah. So good afternoon, everyone. Welcome to the last lecture of the mini school on geometric approach to quantum mechanics. Our lecturer is again Fabio Anzà. Fabio, we are very happy that you took the time for us to prepare this course, but I hope I can share with the participants that we are planning to use this course for a forthcoming book that you're writing on this topic, and that you're using us as to test the approach. Yeah? Yeah. So we are very glad that we could help you in this respect, and Fabio asked me to share with the participants that if you have feedback for him on how you liked or did not like the presentation, he is very happy to receive the feedback. Yeah. So Fabio, thank you very much. As usual, to the participant, please make use of the Q&A for the questions, or raise your hand, and Ida and I will give you the right to speak and ask the question in person. Yeah, Fabio, please, without further ado, you're already sharing your iPad with us. You're most welcome to start with your last lecture. Thank you very much.
All right, thank you, Francesco. And yes, as Francesco was saying, I'm planning to write a book on this material, and this set of lectures was actually part of testing which approach would be best, especially for students. So please do let me know if you found some aspect of the material particularly hard to understand, or if there was something that didn't track. I would absolutely love to have this kind of feedback. So the plan for today's lecture is kind of split in two parts. We'll go through a quick recap of not just lecture 3, but what we did in the first 3 lectures. And then the main theme will be kind of trying to answer what we can do with this. And really, this is my personal answer, in the sense that this is what I've listed here is a bunch of ideas that include what I've done with it. So it's part of the work that I've been doing for the past year and a half, but also what I would like to do with it. So I'm going to tie this back to what I said in the first lectures, that if people are interested in pursuing any of these ideas, I'm absolutely happy to discuss collaborations. All right, so let's begin. So what did we, really quick summary about what we learned in the first 3 lectures. So geometric quantum mechanics, actually standard quantum mechanics, as we said, is grounded on the linear algebraic approach, right? We have states that belong to a Hilbert space. Observables are Hermitian self-adjoint operators that have real eigenvalues, and the evolution, the most fundamental evolution is given by Schrödinger's equation, where H is the Hamiltonian. However, we kind of started saying that the Hilbert space description contains some redundancies. And I've mentioned the redundancy in the phase, but there's actually an additional redundancy, which is in the way you write a density matrix. And in order to get rid of these redundancies, what you can do is you can go into geometric quantum mechanics, which identifies the full quantum state space with, at least for finite dimensional quantum system, a complex projective space of dimension n, where n is d-1 and d is the dimension of the Hilbert space. So we go from a picture in which states are kind of like vector in a space to a picture in which states are points in a manifold. And basically what we did is to study the rules, the geometry of this manifold, and it's the dynamics, the Hamiltonian dynamics on this manifold. We learned that the particular geometry of the complex projective space is actually responsible for the quantumness of the theory, in the sense that if you look at its geometry, it has two distinct characters. One is symplectic, and the other one is Riemannian. And the symplectic aspect of its geometry ties it back to classical phase space. In classical mechanics is formulated in terms of symplectic geometry, X and P and Poisson brackets and canonically conjugated variables and all of that. And complex projective space has this structure in it, and it's given by its fundamental properties. As we said at the beginning, this is given by the fact that the complex projective spaces are Kähler spaces. So they have these two notions of geometry intertwined with each other. The notion of Riemannian geometry has to do with the fact that in quantum mechanics, there is a fundamental notion of distance, which is given by the Fubini-Studi distance, that kind of builds up the state space. And these two notions of geometry kind of work together to provide the beautiful intricateness of the quantum state space. All right, so this was the kind of the making this rigorous was the goal of the first kind of first two lectures. And then we discussed how do you do essentially how do you do statistical mechanics and integrals on this quantum state space. And we developed this, we use measure theory essentially. And so I introduced this concept of a random quantum variable. What does this mean? This means the following. As we said, in this quantum state space, a point is a pure state. But being a pure state, we can always think about it. We can always, as we do in classical statistical mechanics, instead of thinking about particles moving on a space, we think about points as probability distribution that have the full probability mass concentrated on a single point. And in this way, we do the switch from points that move on a manifold to probability distribution that evolve on a manifold. And these probability distributions basically are what I call geometric quantum states. Quantum state. And what they do is that they, as for any probability theory, they help us deal with uncertainty and disorder and lack of knowledge. All the cases above. Geometric quantum, the notion of geometric quantum state is going to be relevant for all the cases above. But the idea is that when you don't have full knowledge about the state of the system, which means that maybe the system is not in a pure state, you have a certain probability distribution of these belonging, to a certain region. And the way we interpret this through probability theory is that there is a random variable that we call Z that belongs to CPN. And this random variable, of course, has a certain probability density function, Q of Z. Actually, to be more precise, dP around Z is Q of Z dV Fubini studi Z, right? So this means that Q of Z is the infinitesimal, is the probability density of finding the state of the system in a certain region of infinitesimally small Fubini studi volume element. All right, so this means that well, this connection, the fact that Z, we can think of Z as a random variable with a certain probability distribution. We indicate it as usual, as we do in probability theory, in the following way. What else have we done? We have looked at what is this Q, right, in particular cases. And the case I am most interested in, but I also think it's actually relevant in a lot of cases, is the case of an open quantum system. So what is an open quantum system? It's a system built in the following way. We have a huge system that includes ours and the environment, and the whole system is isolated, but we're interested in a small part of it, S, and this part interacts with the environment, right? So when this happens, the state of the system, S, is not pure, and so it's going to be described by some probability distribution. What is this probability distribution? And I'll show you how you can build it. And essentially, you build it in the following way. You can write the full pure state in this way, where E alpha is a basis for the environment. And the ensemble that you get in this way is the following. Q of Z is sum over alpha, Y alpha, delta tilde of Z minus Z alpha. So this is essentially a convex sum of Dirac deltas, which means that if I look, if this is a cartoon of my state space, this is kind of how it looks like, right? There is a bunch of points in here, and these are the Z alpha, where alpha goes from 1 to the dimension of the environment. And each of these Z alpha carries with it a physical property, which is probability mass. And so as a result of the dynamic, these points are going to move around, and we're going to have an information dynamic, a dynamic of probability masses on the quantum state space. All right. So this was as far as geometric quantum state goes. Oh yes, we introduced, in last lecture we looked at three kind of fundamental ensemble, right? The pure state, which is a single point, so a Dirac delta concentrated in one point. These example of a finite number of Dirac deltas in a convex sum, each one of them carrying some finite probability mass Y alpha. But we also introduce some continuous. We said that, right, the probability density doesn't necessarily have to be given by a distribution. It can be given by a continuous smooth function, like, for example, the case of a Gibbs distribution. And the case of a Gibbs distribution is actually quite simple, because if you have a Hamiltonian in terms of the operator, the energy function associated with it, E of Z, is just Z H Z normalized Z Z. And this means that Q, a thermal equilibrium of Z, should be something along the lines of e to the minus beta E Z divided by the integral with the Fubini studi volume element, e to the minus beta E Z. Right, so these were the three examples that we discussed. All right, so this is as far as kind of a quick recap of how these tools work, and I'm not obviously not going to go into the details, but we discussed those details in the first 3 lectures, and obviously please feel free to ask me any question about it. All right, so for today, the first thing that I prepared is, let me switch my sharing to this. All right, so this is a simulation, and I'm going to go through this example because I think there's a lot of, it's very rich in terms of visual cues. So I think it's quite useful to have this example in mind to understand what it means to analyze finite dimensional quantum systems, in particular open quantum systems, with this formalism. So this is an example in which is an example of an open quantum system in which I have a single qubit that interacts with the number of qubit that is, I think in this example, this is 10. So the total thing is 11 qubits. And we begin in a tensor product situation in which the system is completely independent on the state of the environment. But as a result of the interaction between our qubit and the environment acts on the qubit and changes its state. How does it do that? It does that in the following way. So what you're looking at, each one of these points are the Dirac deltas, right? The position of the point is given by the coordinate of z alpha, and the color of the point is given by the probability mass y alpha. And as you can see, there is a lot of this is very rich, and it has a certain structure, right? So the idea would be that one of the things that I've started doing is to try to understand what kind of dynamical equations govern the equilibrium of these points. But this is actually a matter for a bit later. What I want to start with is something that is fairly simple, and it's what I call geometric quantum thermodynamics. And the example that I've built is here. So here, I'm comparing 2 different situations, right? So in equilibrium physics, and typically in systems that exchange energy with their environment, what we do is that we use the thermal equilibrium assumption, right? By using the thermal equilibrium assumption, what we do is that we assume that classically, what we do is that we take the phase space and we put Gibbs probability distribution on this phase space, and this is supposed to describe the long time behavior or the time averaged behavior of our system. And in certain cases, you can prove this rigorously, that irrespectively of what happens, of which initial state you begin with, you're going to end up in a situation which is described to a fairly good approximation by a canonical measure, e to the minus beta, the energy. Now, if you do that in quantum statistical mechanics for finite dimensional quantum systems, the standard approach is to take a density matrix that is diagonal in the energy eigenbasis. What this means is that there is no probability of transitioning from one eigenstate of the local Hamiltonian to another one. And everything is basically described by a classical probability distribution that is given by basically Maxwell-Boltzmann rule. Now, this corresponds to, we can use this and we can analyze this in geometric quantum mechanics, and this is done on the left-hand side, right? This is an example of a Gibbs measure that describes a density matrix that is diagonal in the energy eigenbasis. What this means is that when you choose the ensemble that is that basically describes the eigenvectors of the Hamiltonian. What you're implicitly doing is that you're putting zero probability on all the other points, right? Because let's remember, this does not correspond to the probability that if I make a measurement, I get some of this result. This is the probability that before the measurement, the state of the system was there. So in this case, by using the standard formulas, we end up with a geometric quantum state that is equal to the one you see on the left. And as you can see, there are only 2 points that contain the whole probability mass, and these corresponds to the specific eigenstates of the local Hamiltonian for, in this case, for a qubit, because this is a 2-dimensional quantum state space. On the right-hand side, instead, what you have is a geometric canonical measure in which, instead of assuming that Boltzmann rules essentially holds only for the eigenstates, you assume the Boltzmann rule holds the fact that basically the log of the ratio of any 2 probabilities is essentially given by the difference in energy. This is Boltzmann rule. If you assume the Boltzmann rule holds in basically for the whole state space, not just for the energy eigenstates, then you end up with a completely different canonical measure, completely different geometric quantum state, and a slightly different density matrix. And this is depicted on the right. Despite the fact that this ensemble gives you a density matrix that it's not a Gibbs density matrix, this does depend on one parameter, that is beta, the inverse temperature. And you can actually plot measurement outcomes that you assume that you're making some measurement on the system, and you plot the behavior of the measurement as a function of beta. And this is actually the result. Sorry, it's a bit pixelated. But on the left-hand side, what you're looking at is the expectation value of sigma z compared to the left and right case for these 2 ensemble. The orange one is the one on the right, and the blue one is the one given by the standard quantum statistical mechanics. So you can tell that basically there is qualitatively it's the same kind of behavior. It's monotonically decreasing with the temperature, but there is a quantitative difference that can be appreciated with measurement, and thus can be measured in a lab. So these 2 provide these 2 notions of thermization, which is basically assuming that the probability density is given by one of these 2 ensembles. They actually give you different phenomenology, but despite that, you can actually prove that they give you that thermodynamic rules in terms of first law, second law, even fluctuation theorems, it holds in both cases, which is something that I find very, very interesting. So while it does hold in both cases, there are obviously some differences. The first one being this, in the sense that if you actually make measurements, you get slightly different results. And yet, despite the fact that you get different results, either way, the thermodynamic reasoning still holds to a very good degree of accuracy either way. And you can define notions of heat, work, entropy, and so on and so forth. Now, whether one of these pictures is accurate, this is ultimately a question about dynamics, right? So given a certain initial condition for my system and the environment, I let it evolve, I let the whole system evolve, and I look at the geometric quantum state of my subsystem as a function of time. Does it ultimately evolve into one of these pictures? Now, the question, this is implicitly a question about thermization, which is still an open question, despite the fact that we started using thermal equilibrium assumptions more than a century ago. But the general conditions that lead to thermalization are still not known. There's obviously a huge amount of literature on this, and I don't want to downplay any of the recent developments, because the advent of quantum information theory has kind of sparked new life into this research on thermal equilibrium, which is a problem that I find extremely interesting because it ties to a lot of aspects of the dynamic. So at the end of the day, whether any of this is the right approach to describe a system after the transient, this is a question about the dynamic, which I am very interested in studying, and that I'm currently studying. But yeah, with this, you can do a lot of analysis on your own, because truly this is just a probability. These are just probability distribution in a two-dimensional space. So what you can do is that you can think about slowly changing your Hamiltonian and seeing how the system, for example, adapts to external perturbations. And obviously, the answer is going to be most likely different in the two cases. So is there a way to discriminate beyond, say, solving the full dynamic to tell if any one of this distribution is the correct one, at least in some cases? This is a question of which I do not know the general answer, but I'm very interested in it. Now, in order to, this was kind of the first thing that I did with geometrical quantum mechanics. The second thing is goes back to these examples that I've discussed a couple of times here, and it's about trying to understand what are the equilibrium equations that govern this behavior. Now, this is I think it's a very interesting problem because it connects the quantum phenomenology, because this is quantum phenomenology, with the theory of dynamical systems with differential geometry. So it's a beautiful, I think it's a beautiful problem to kind of solve in general. But I've given a tentative theory of it, and well, okay, what you can certainly say is the following. Because of the fact that probability is conserved, right? Probability sums to 1 at each time. Because of the fact that probability is conserved, what you have is that you have a continuity equation, right? Whenever you have a globally conserved quantity, but not, you have a globally conserved quantity on an extended space. Because of the dynamic, the density of this property will be shifted around by the dynamics of the system or of the environment. And what is happening here is that basically there are three forces, well, there are two kinds of forces at play. There's one force that is given by the local Hamiltonian that tries to move the point always in the same direction. And then there are two major forces that we can see acting on the system that are trying to pull the system in different direction. And as a result of this pulling in different direction, the probability mass that was first concentrated in a single point gets split into different points, right? Now, the bare mechanism that you have to basically set up a continuity equation are the two following. One is a flux mechanism, right? There is a point. If we look, this is a cartoon of the quantum state space, the projective Hilbert space, P of H, and we have a bunch of points on this manifold. And if you draw a closed circle, let's say that this is two-dimensional, as in the case of the qubit. If you draw a line and you enclose a certain number of particles, you can ask the question, right? How many particles on average am I going to have in this region? So what's going to happen over time, if you fix this region, is that you're going to see that there are particles that are in the region that go out, and that there are particles outside the region that go in. this is a flux, right? So the probability evolution, if each of these particles carries some physical quality with it, could be charge, could be mass, could be angular momentum. You know, this is the standard way in which you build the transport theories for non-equilibrium behavior. In this case, this is probability mass. And so here, this way of thinking leads you to define a notion of probability flux, right? There is a constant, well, it's not always constant, but there is a flux. There's an influx and there is an outflux of probability mass that is given by the number of particles that come in and come out, times the total probability mass that they, the average probability mass that they carry. And this is one of the mechanisms in which the probability density can change. The other one is given by it's a source mechanism, right? So in this case, let's assume, for example, to kind of understand why these two can be studied kind of independently, but they're obviously related to each other in a general situation. Imagine that each one of the points carries a fixed probability mass, right? There is no change. The y alpha, the probability mass that each of the point carries, it does not depend on the point. So it's just 1 over the number of points. So because that quantity is fixed, then this moving points around is the only way the environment can act on the system to change its state. On the contrary, there's a kind of an opposite way of thinking in which you imagine that the points are fixed in quantum state space, right? So in principle, there shouldn't be any dynamic. However, because of the fact that the y alpha, the probability mass themselves, they can depend on time, and this is very different actually from standard transport theory, even though there are phenomenological analogies you can draw from. So even in this case in which the points are fixed, you can still appreciate some dynamics in the quantum state space. For example, when two points exchange probability mass with each other. So let's make a simple model in which the sum of x alpha of t and x alpha of t and x beta of t is constant, and in this case I should call it y, but that's okay. This is the probability mass. So if this is constant, as a function of time, you can have situations in which a certain amount of probability mass is basically transferred to a point that in quantum state space is it's very far away. So this can be a highly non-local mechanism for the transfer of mass, and this does give rise to an incredibly rich phenomenology that we still need to fully understand. The flip side of understanding this phenomenology is that because of the way this geometric quantum state is built, this is essentially a representation for the full evolution of the global wave function, in the sense that it retains way more details about the structure of the evolution than a density matrix does. And so essentially what you can do in this situation is to write let me go back to the iPad. All right, so because of this analysis, you can essentially, if Q of Z is, sum over alpha, Y alpha of T, delta tilde Z minus Z alpha of T, then you can prove that dq Z in the T plus the divergence of the probability flux is equal to the source term, and this all depends on time and on position, actually, on the quantum state space. So this is a function of Z, and this is sigma t of z, and you can prove that the flow, the flux has the following form. Oh, sorry. Flux has the following form. Sum over alpha z alpha dot, and this is actually, let me write it like this, in the t, dz alpha in the t, delta tilde of z minus z alpha of t, and there is y alpha of t. And then sigma t of z is just sum over alpha of y alpha dot delta of z minus z alpha of t. So this is essentially a continuity equation for probability transport on quantum state space. And I'm planning, and I am using this to study essentially probability flows in quantum state space in various situations. Now, there are at least 2, if not more, kind of large problems that I think are that this can help a lot with. One, we already discussed it, is kind of trying to understand non-equilibrium dynamics, in the sense that obviously, as it happens in classical statistical mechanics, if we have a huge number of particles in our system, it's just impossible to keep track of all of them, right? So what we need to do is come up with reliable dynamical models for some coarse-grained macroscopic quantities, and these that have a very specific physical meaning. And these are exactly what probability flux and the source and the sigma term are. We know exactly their physical meaning. We kind of understood before what they relate to, in the sense that they are part of the continuity equation. And so building phenomenologically relevant models for probability flux and probability source sourcing term, I think it's going to be a very, very rich area, because this is the way across the past century we built essentially transport theories, and it has been incredibly successful in a lot of cases. So I do believe that this technique can be very, very, very powerful. So this is the first case. The second case is kind of more technologically oriented, and it's about trying to optimize quantum algorithms. So obviously, this model of an open system, right, SE, can actually be used to study quantum hardware, or in general any quantum system. You have a situation in which you're trying to build a quantum computer, a computer that works with hardware that works at the quantum in a fully quantum regime, and obviously this is very hard, but there is a huge amount of people involved in trying to do it, and kind of trying to develop the hardware on the one side and the software on the other side. But where this technique I believe can come in handy is in trying to design algorithms and optimize them. The reason why I think so is because essentially the organization of the points in here is a representation of the full wave function, right? So in some sense, what you can do is, if you imagine you have a quantum hardware built in the following way: you have a certain processing unit, and you have a system which is where the results of your measurements will be, where you will measure basically the processor and try to extract the classical information once it has been computed with the hardware. Now, if we could look at the distribution of basically the measurement results before making the measurement, then we might have a way to optimize the algorithm. And this is exactly what geometric quantum mechanics can do in this sense, in this case, because each one of these points, if you remember, if we have sum over alpha y alpha delta z minus z alpha of t, then what you have is that the global wave function is sum over alpha square root of y alpha e alpha. And this, in a quantum hardware, these are known because these are basically the states that the system, that the environment uses to compute the answer. So this is a controlled system. So we do have access to this, which means that in principle, we could maybe not reconstruct the whole wave function through numerics, but definitely gain a lot of insights about what exactly a quantum computer does when it processes information. All right, so this is, I still have some time, 20 minutes, and I still have some material to cover. So I'm just going to move on to a related example. Nope. This is the one. This is another example of the same behavior, just with a different kind of visualization. And this is not the 3D. It's not the 3D modeling, but this is just in 2D. And the probability mass that these are the the Dirac deltas, the points, and the size of the circle that you see and the left is essentially the amount of probability mass that each one of the point carries. And as you can see, there is some kind of self-consistent behavior in which the system can naturally organize around this lower region around phi equal pi and p equals 0. All right. If you are interested, for example, in the long time behavior of this system, what you do is that you take the left-hand side and you do a time average, and you ask what is the time average geometric quantum state, and this is your answer. This is actually a coarse grain, obviously, coarse grain version of it, but you can tell that it's kind of, let me put it here. You can tell that it's kind of related because this point here is close to p equals 0 and some phi around pi, which is exactly this region here where the big dots, the bit dots are. Now, again, this is an example of how you study, for example, thermal equilibrium, thermalization, or problems of ergodicity, long time behavior, and so on and so forth. Yes, last example, I just want to show a simplified, this is a very simple model compared to all the other ones. In this case, the particles interact. So what you see in the top left corner is an actual representation of the system. So I'm just trying to describe, I guess you would call it a gas of qubits, in which these are classical particles. So they have a position and a velocity, but inside of them, there is a quantum feature, which is a two-level system. And what they do is that they interact in a essentially in a mean field way with a magnetic Hamiltonian. So it's just the spin, scalar, the dimension of the magnetic field, and the magnetic field that they feel at every time step is given by the average of the magnetic field of the spin carried by the points surrounding it. And as you can tell, basically we begin in a situation, okay, so this is the top left. In the top right, you actually have the geometric quantum state. So the geometric quantum state of the internal quantum degrees of freedom, it starts, they're simply 2 points. Well, there's a lot of points, but they concentrate on 2 regions. And these 2 regions kind of evolve coherently over time for an appreciably amount of time. But as you can tell, the structure of the geometrical state starts to kind of degrade. And in the bottom left, you have the another representation of the geometric quantum state in terms of the probability mass that we observe in each one of the regions. This is essentially, the bottom left is essentially a coarse-grained version of the top right. And in this case, there is no probability source term, but if you see in the bottom right, what I'm showing is the vector field given by the information flux. So this is essentially the vector field that each one of these points feels as a result of its interaction with all the other particles. And I'm just going to speed it up a bit. So you see, actually, let's do it like this. You see that basically the point starts in a very orderly fashion, and then after some time scale that still needs to be characterized, they completely lose coherence, and they start behaving erratically, as one would expect from some kind of stochastic model, right? So it makes sense that if one averages this distribution over time, you're just going to get something that is flat because of some kind of ergodic property. There's nothing really too interesting after this time scale. All right, so as you can see, I mean, there is, I believe, a very rich phenomenology that one can study, understand, and it has both purely physical scientific relevance and also applied, technologically applied relevance. All right, let's go back to the iPad and continue our general discussion. So I've covered, what I'm covering right now and for the next 3 minutes is going to be what I've done with it. You know, since the question is what we can do with it, what can we do with it? I've covered what I've done with it, and then I'm going to cover what I plan and what I think is interesting to do with it. So there is a couple of other really interesting aspects. One is the notion of the connection with classical statistical mechanics and analog information theory. So the idea is exemplified by the notion of entropy, right? In quantum mechanics, we have, as in classical, we have different notions of entropy. But for a quantum system, kind of the prime one is given by von Neumann entropy, which is minus trace of rho log rho. But this is obviously not appropriate to address the entropy of our geometric quantum state. But if we have a geometric quantum state, what we can do is we can associate to it a geometric entropy, which is the so-called differential entropy, is the integral with the Fubini-Study measure of Q log Q, right? And this quantity is actually well defined, and you can compute it exactly, especially if the probability distribution is smooth, but you can actually extract its value even when the probability distribution is just a convex sum of Dirac delta, because in that case, this is just going to be minus sum over alpha y alpha log of y alpha. But obviously, this notion of entropy is different than the von Neumann entropy, but you can actually prove that it's lower bounded by the von Neumann entropy, but it raises some question, right? On the one hand, this is very, very reminiscent of Gibbs and Boltzmann's entropy, right? The integral on the phase space of probability of x and actually f of x and p log of f of x and p, and this is the quantity, for example, that Boltzmann used to prove his H theorem. And so this is a quantity that has a lot of fundamental relevance, and its quantum counterpart, its direct quantum counterpart, is actually not the von Neumann entropy, but it's this geometric entropy, right? Because this is a classical notion of entropy for the quantum state space, right? So this is literally the closest analog to the notion of Boltzmann entropy. And how it evolves, is there an H theorem for it, right? The physics of it is obviously different, because here people are studying, you know, position and momentum, but here you're studying probabilities and phases. So whether there's an H theorem here, it's I don't know the answer to that. But it's I think it's a very interesting problem, and it's very relevant for issues of thermalization, for example. Now, of course, I've started with entropy, but especially in the past 20 years, you know, the connection between thermodynamics and information theory has really strengthened, has become much, much stronger. And so exactly in the same way in which we can extend the notion of entropy into geometric quantum mechanics, you can imagine to look at way more general, at a general information theoretic approach that is based on analog information theory, not on discrete information theory. The reason why this might be relevant is because the quantum state space, it's actually not discrete, it's continuous, right? So there can be advantages in studying these kinds of problems, and in looking at this problem through the lens of classical, well, analog information theory for continuous variables in this, for quantum system in this peculiar sense, in using geometric quantum mechanics. Now, a notion of mutual information has been defined, but for example, I haven't studied it in dynamical situations. For example, this idea allows us to answer really interesting questions that are a bit harder to pose and to answer with the standard formulas. For example, in our case of a qubit, right, we have two variables, p and phi. P kind of stands for probabilities and phi stands for phases. But in the general situation, what you have is a probability vector and a phase vector, right? There is a lot of them. And a really interesting question is, if I have full knowledge of the probability part, how much knowledge do I have about the phase part, right? Because this probability and phase splitting is put there by a choice of a reference basis in the Hilbert space, which is a set of reference points in the quantum state space, which means that behind this, there is a choice of a complete set of commuting observables that tells me essentially, that allows me to write a basis. Now, because of the non-commutativity we have in quantum mechanics, these quantities, the amount of information that they have about each other is carried over by non-commutativity. And so I think it's very interesting, for example, to study probability phase, the mutual information that probabilities have with respect to phase, and problems like this one, in which the standard way of asking this question from the perspective of standard quantum mechanics would be, I think, a bit harder and much harder to solve. All right. We've discussed entropy, problems of equilibration and thermalization, and ergodicity, mutual information. Yes, there is a notion of quantum information dimension that you can define. And let me, this is actually a paper that's currently it's currently being reviewed. And
sorry, Fabio.
yeah.
Do you mind answering the question of Jean?
Oh, sorry, I didn't see that there was a question.
Yeah,
sure. Yeah. Thank you, Leo.
Thank you. So for the equation you wrote down for the entropy, if I remember correctly, and this might be what you meant by the difference between analog and discrete information theory, but if I remember correctly, Shannon generalized his information entropy, the Shannon entropy, in that same way to the integral. But if I remember correctly, that turned out to be incorrect.
Yes, you're right, but it's not incorrect. Is not as general as we like, in the sense that it has some pathologies, right? And this happens whenever you do have a quantum state, well, a state space or a sampling space, to use random variable nomenclature. So this happens every time you have a sampling space that it's continuous. But for example, if we have a probability distribution in one dimension, P of x, you can do the integral P of x log P of x dx. And this quantity can be negative, for example. And this, which is not true for finite dimensional systems, right? Now, there are the answers to this question. First of all, you're not the first one to pose this question, and this is a very important question. And it has basically inspired people to write different definitions of the notion of entropy, which try to extend the notion of finite dimensional into infinite dimensional in various ways, trying to catch on different things. There are a couple of things that I can say about this. First, while the notion of differential entropy might have problems in a sampling space in general, I think that in our particular case, this is not a problem, because the essentially the algebra of the volume element is not up to us. It's not like we can do any transformation of coordinates, but there are certain transformations that don't make sense, right? Like, for example, and that's because the space is bounded, right? So the quantum state space is compact. It's a sphere, right? So it really, for example, if our coordinate is theta, it's our theta and phi belong to 0 and 2 pi. Sure, you can find new coordinate system, but it really doesn't make any sense to build a coordinate system in which, instead of looking at theta, you look at 137 times sine theta, right? So there are the physical information about how you build the volume element, and then notion of entropy provides you with more information that partially fix this problem. Now, obviously, they don't fix it at all, because the math is just the math. So you know that this point is there, but you do have a physically relevant way to fix this. And I mean, it's just too long, and my answer is already long. But there is a way to kind of take care of this. And the way you do this is basically by always referring to basically by setting a reference measure on the quantum state space. So by declaring essentially what is the uniform distribution on your state space, which is something that is physically motivated and very easy to answer in these physically relevant cases. And then once you have that reference measure, you can refer everything to that measure, and then things don't depend, this problem it's not there anymore, because you use tricks like relative entropy to get rid of the quantities that might change as a result of the change in the coordinate system. But let me remind you that the way I built this is actually so that these quantities should be independent on the, basically on the reference frame that you choose, on the coordinate system that you choose. So there are ways to deal with this apparent problem. One of the actually most accurate ways that I do know how to do this is essentially what I did in this paper that I'm about to show you. Can you see the screen? This paper?
Yes, we can, Fabio. We can,
okay.
Yeah.
So in the way you deal with this problem is by essentially, where is it? Yes, so this is an example of a probability distribution. So imagine, sorry, this is our quantum state space, P and phi, and imagine that you do the following. Instead of defining directly the integral, what you do is that you have your probability distribution, you chop your quantum state space in cells, very small cells, and you ask how much probability do they carry, right? And now what you do is that you change the size of the cell to something smaller, and then smaller, and then smaller, and then smaller, and you look at the rates of basically how these things change. And this concept was developed by Rennie, and it's about partially solving the problem that Jean was mentioning, but also about defining notions of basically the local dimension for a certain probability distribution. Now, the interesting thing is that through this technique, you can actually see that there are certain probability distributions that are very relevant in physical cases that have there are certain geometric quantum states that have fractal distribution, like this example that reminds you of a Cantor set and has an information dimension that it's not an integer. So this is like an object that has a fractional dimension, and you can get it. Well, where is, yes, this is the one. You can actually get it in really interesting physical situations, like where is it? This is another example of a Cantor set in which you have, in this first case, you have a certain number of islands here of probability, but if you look inside these islands, you have internal organization in terms of smaller islands, and then so on and so forth. And so you have this nested structure that are typical of fractals. And this is a geometric quantum state that you get in the thermodynamic limit, or up to numerical simulations I could do for increasingly large environment size, for the ground state of a certain local Hamiltonian, in which I've removed a symmetry. So I take a Hamiltonian with a certain symmetry, compute the ground state, take the Hamiltonian with a certain symmetry, remove the symmetry by changing one local interaction, and then ask about the geometric quantum state of the ground state. And then you get fractal structure in full kind of analogy with the idea that these structures should emerge by breaking some kind of symmetries. All right, I'm already over time, but before I go, I really want to mention very briefly the other thing that are possible, that I believe are possible and are very interesting to do. There are some really interesting connection with entanglement theory, in the sense that a lot of entanglement is one of the distinguishing feature of quantum mechanics. So it's very interesting to look at it from the geometric perspective. And the hope is that these geometric tools are going to allow us to build a better intuition about multipartite entanglement. This is one of the hopes. The other one is that entanglement theory involves coming up with ways of quantify the amount of entanglement in a certain system. And for states that are not pure, this can be practically, conceptually simple. There exist so-called convex roof constructions that involve some kind of optimization. But solving this optimization problem, it's very, very hard. But this is exactly what geometric formalisms do best. This is why they have been incredibly useful in kind of modeling stochastic descent and other kinds of algorithms. So the idea is that it should be possible to use geometric quantum mechanics to look at these optimization problems in a physically relevant way by basically scanning among all the possible geometric quantum states with a certain density matrix and understanding whether there is some convexity that helps closing the optimization in an analytical or semi-analytical way. Now there are fundamental problems of quantum mechanics. I find them very, very interesting. I have been studying the emergence of classical behavior with a graduate student and some colleagues at Maryland and at Davis. And we're doing this through the notion of quantum Darwinism, which is kind of building up on the theory of decoherence that Zurek and collaborators and a lot of other people have developed. Now, there are questions about collapse and unitary evolution that would be very interesting to look at them from the perspective of geometric quantum mechanics, because those are different kinds of dynamics. So they impose very different evolution rules on the geometric quantum states. So the hope is that by carefully looking at these different, at their difference, one can understand how they're connected. The final two things are state preparation and assessing resources. I'm not going to comment too much on this, but suffice to say that you can use the geometric formalism in physical situations in which your density matrix, you have two different physical situations in which you're trying to build the same density matrix, but with different resources, and you need to assess the various ways in which these resources can be combined to build your density matrix. And geometric quantum states are perfect for this because they are the ensemble. One of their interpretation is as the ensemble behind the density matrix. And so different ensembles will give you different resources. And so you can use geometric quantum states to deal with this problem. And there are more general questions about the connection with the theory of dynamical systems, and in particular, really interesting opportunities like, for example, the ability that we have to define Lyapunov exponents in this quantum state space, which is something that for a quantum system, it's really still not very clear how to do, and if you do, what it really means. And that's essentially because of the peculiarity of the unitary evolution. And there is a really interesting aspect here, which is that unitary evolution, which, you know, in quantum mechanics, we think of them as Hamiltonian evolution. We can actually have Hamiltonian evolutions in geometric quantum mechanics, so objects that evolve with a certain Hamiltonian, whose evolution is not unitary. Now, I think that this is a very interesting opportunity because those systems can be studied with the same geometric technique, but they don't belong to the standard category of unitarily evolving quantum systems. So they can be used to model, for example, systems that evolve with nonlinear Schrödinger's equation and other situations. These are relevant, for example, in phase transitions where you have Landau-Ginzburg kind of equation. All right, I think I've expired my time, and I'm actually 10 minutes over. So I really want to thank you for the time you spent listening to me, and I hope the material was interesting. And as I said at the beginning, please do reach out with questions, and if you're interested or just with feedbacks, I would be most happy to hear about them.
Yeah, Fabio, thank you very much. Nothing to worry about. The 10 minutes over time, you know, we are flexible, and the topic is so interesting that I think nobody minds.
Thank you.
Thank you very much.
So
we have to thank you for your time, and also for waking up early in your part of the world, to be with us.
It's okay.
So thank you very much. We really appreciate your effort. I think we had the odd question in between. I don't know, Ilya, do you know if there are any questions in the Q&A, or if participants are happy to raise their hands to ask some final question or give some final feedback to Fabio?
Because there is no questions in Q&A, neither in the chat, unless somebody wants to raise their hand.
Maybe I can ask you a question. You know, Fabio, it's always in, you spoke a lot about open quantum systems, yeah? And there is now, I think there are some efforts going on to try to simulate open quantum systems on the existing quantum computing hardware. Yeah.
Yeah.
Do you have the feeling that approaching this problem from your geometrical point of view could open up some new avenues to come up with something interesting?
I certainly hope so. So I think about this, in general, I think about computation as a dual perspective, right? There is the perspective in which computation is a set of rules that you can extract to understand your dynamic, right? So, and this is more like machine learning kind of approach, right? You have a set of, you have a system that evolves, does its own thing, and you're trying to extract the rules. I personally think that the geometric approach would be most helpful in that sense. Now, the flip side is obviously, if it is truly powerful, and that is yet to be seen, then you can, in principle, leverage those things, those ideas, to simulate it in a simpler fashion. However, whether you can build basically an open quantum system simulators that it's founded on the concept of geometric quantum mechanics, I do not know off the top of my head the answer, because truly the advantages of it, the experimental advantages of the linearity of quantum mechanics, I mean, we all know that this is where a lot of the advantages of quantum comes from. So I don't think it's that straightforward. However, and that's also right, making effective simulations about open quantum systems, it's about getting rid of the right degrees of freedom, right? So that your representation is accurate, but you don't have a lot of baggage with it. This has a lot of baggage because it's a huge, in principle, if you want to follow each one and every point, it's a huge memory overhead. However, in the truly infinite limit, right? If we imagine that our environment is truly infinite, I do think that this can really help, because in that limit where you have just a huge amount of points, and this is going to be like a continuous probability field, then what you can prove is that the evolution is of the geometric quantum state, it's always Markovian. Yeah. Because essentially you're controlling every single state, right? So even in the limit, this should retain some Markovity, but it could be insanely complicated, right? Because in principle, you're describing the evolution of the whole wave function. So this is going to be, so I think it has the potential to do that, but I don't think that is going to be true in general. I think it will help in certain cases, and it will help in trying to extract knowledge from open quantum systems. This is my feeling, but I really don't have the full answer yet.
I also would like to have the answer, but I don't have.
Right.
But it's an interesting topic anyway. Yeah. Okay, no, fantastic. I see there is a raised hand, and please, you're welcome to ask your question or make your comment.
Hello?
Yeah, please,
Hi.
go ahead. Hi.
Hello? Are you
hearing
me?
I hear you.
Yeah.
Yeah, good. Thank you for your presentation.
Sure.
on the geometry, quantum thermodynamics, quantum system. Looking through all the terminologies, I discovered that I need to know more of this so that I can be able to fit in into your research area. So I don't know if you can make some of your presentations available so that I can brush up, I can go through them, and I'll be able to collaborate in the nearest future.
Absolutely. So this is, yes, I can. I don't have it now. So as I said at the beginning, I'm going to use the material I've developed for this set of lectures to write a book. But this is there's going to be lecture notes before that book, and so these. My sense is that I was waiting for the class to end to start writing because I wanted to have some feedback. So my sense is that I should be able to have some notes by the end of next month. Okay. And so
Thank you very much.
And I would be more than happy to discuss any collaboration. So you can, I mean, I don't know if the email is available, but you can easily reach out like mid-month or at the end of the month, and I can keep you posted on, you know, how the lecture notes are progressing. And maybe, you know, if I finish the first one or the first two, I can send them over for you.
Thank you. Thank you very much.
My pleasure. Sure.
Thank you very much, Fabio. And also maybe a reminder to the participants that we've recorded all the lectures. And the previous 3 are already on our YouTube channel, and this will be there latest by tomorrow. Yeah, so that if you have lecture notes that you're planning to post online, Fabio, just share the link with us, and we can link it with the videos if it is interesting for you. Yeah, that
absolutely. I would love that.
One line of code. Yeah, that's easy. Yeah, excellent. So if there are no more questions, Fabio, again, from all of us, thank you very much. I see some of the participants are thanking you profusely in the chat. I will download the chat so that you can read later who thanks you and so on and so forth. Yeah, also for the 3 lectures. I will do it later today. Yeah. Okay, then Fabio, thank you very much. Enjoy your day that just started.
Thank you.
And we are looking forward to our dinner just now. Yeah. Okay. No, fantastic. Thank you very much.
Have a good night. Thank you again.
Thank you, Ilya, and thank you to all the participants. And sorry, but before I leave, the next mini school in April will be on a slightly different topic. It will be about computer-aided drug design. Yeah. So. You know, sometimes it's useful to look at different things.
Oh, absolutely.
Yeah,
absolutely.
But the announcement should be in all your mailboxes, I guess, latest by tomorrow morning. Yeah, fantastic. Okay, thank you very much, Fabio. Again, thank you very much.
Thank you again
for being with us for the whole month, and have a good rest of the day, and all the best. Yeah, thank you, Fabio. Thank you very much.
Bye. Thank you.
Bye. Bye. Bye.